The population of Adamsville grew from 8,000 to 14,000 in 6 years. Assuming uninhibited exponential growth, what is the expected population in an additional 2 years? So first I want to start by focusing on our assumption that we have uninhibited exponential growth. So that's what's referring to the model that we'll use to answer this question. Uninhibited exponential growth follows this model of A equals A naught e to the kt. Sometimes when we're talking about population, however, they might use P instead of A. So it might look like this. P equals P naught e to the kt. So this is the model that we're going to substitute some of this information in. And in the first sentence, it states that the population grew from 8,000 to 14,000 in 6 years. With just this bit of information, we're going to be able to find K, which stands for the growth rate in this problem. Maybe it's a good idea to start with that. This formula, P equals P naught e to the kt. Let's go over what each one of these stands for. P naught would be our initial population. So P naught is initial population. K is our growth rate. T is time. And then P would be our ending population, or population after time. So using this information in the first sentence, that we grew from 8,000 to 14,000, gives me values for P naught, so our initial population, I apologize, I'm having some trouble with my pen here. So that 8,000 is P naught, our initial or starting population. Then that 14,000 is our population after a time period of 6 years. And so our only unknown value is K, the growth rate. So with that information, we're going to be able to find the growth rate, which is what we need for our model. So we're going to substitute these values into our exponential growth model. P equals P naught e to the kt. In for P, we have 14,000. P naught is 8,000. T is 6, and remember K is our unknown. So once we've substituted in these values, we want to solve for our missing value, which is K. And since our missing value, our variable, is in the exponent, we have an exponential equation, and we'll use our exponential techniques to solve. We first want to isolate the exponential by dividing both sides by 8,000. So this reduces down, those zeros cancel out. We have 14 over 8, and 14 over 8 reduces down to 7 over 4. The 8,000s cancel on the right-hand side, and we're left with e to the 6k. So now we have our exponential isolated, and we want to solve for that k. When we're solving exponential equations, we have 3 main methods for solving those exponential equations. We can make the bases the same. which in this example we can't do. We can convert to a log, or we can take the log of both sides. I prefer to take the log of both sides. So I'm doing natural log on the left and natural log on the right. Once you introduce the logs, you can use log properties, and there's a log property called the power rule, which allows you to move this exponent to the front. It becomes the coefficient, so we have 6k natural log of e. On the other side, I'm just copying down natural log of 7 over 4. Natural log of e is equal to 1. So 1 times 6k is 6k. And then we can divide both sides by 6 to get our value of k. So we have that k equals natural log of 7/4 over 6. I'm going to type this into my calculator to get a decimal approximation. However, I'm probably not going to use that decimal approximation because with these problems, sometimes rounding too early can cause your answer to be wrong later. You want to save your rounding to the end of the problem if you can. So natural log of 7/4 over 6 gives me 0.093. Let's round to 3 decimal places. 0.093. So approximately 0.093. So this is our growth rate. And that growth rate came out to be positive because the population is growing. If the population was getting smaller, that rate, this k, would come out to be negative, and we would call it a decay rate instead. So now that we have the growth rate, we can now answer the second part of the problem. It says, assuming uninhibited exponential growth, what is the expected population in an additional 2 years? So we want to go 2 more years and find out what that population would be. So there are 2 ways that you can go about this. You can, let me write those 2 ways. So you can use an initial population of 8,000, like we did before, and then our time would be 8 years in that case. That's the 6 years plus the 2 additional years. Or you could calculate this problem with your initial amount being 14,000, and then you would, because you've already done the 6 years, you would only use the additional 2 years. Both should get you the same answer, and we'll substitute into our model. So remember that our model is this right here, P equals P naught e to the kt. So that's P equals 8,000 e, and we're going to use that value of k that we found, a natural log of 7/4 over 6 times a time of 8 years. And the other way, we would use an initial population of 14,000 e to the k, that's natural log of 7/4 over 6 times 2. Now, before I enter this in my calculator, I do like to write this a little bit different to make it easier to type in the calculator. I like to put this time in the front. So I'm going to write this as 8 times natural log of 7/4 over 6. And the same thing with this one over here, 14,000 e to the 2 times natural log 7/4 over 6. So we're going to type these in our calculator to get the population with an additional 2 years. We've got 8,000 e to the 8 times natural log. And so the reason why I moved that time to the front is because you have less parentheses that you need when you type this out if you put that 8 in the front. So 8 natural log of 7/4 divided by 6. And we have 16,870. We'll round to the nearest person, so that's 16,871. And let's type the other one to make sure it comes out to be the same amount. We have 14,000 e to the 2 times natural log of 7/4 divided by 6. And you can see we got the same value under both scenarios. All right, so we've answered the question. The expected population in additional 2 years is 16,871. Thank you for checking out my videos. Have a great day.